Hello girls and guys, and welcome to this interesting video. In this video we're going to talk about the gradient descent, which is an optimization algorithm. In this video we will take a look at the intuition behind a gradient descent for a linear regression, and at last but not the least we'll implement our gradient descent from very scratch. So first of all, what is a gradient descent? Gradient descent is an optimization algorithm which optimizes our parameters or theta values. In short, you can say that it helps in minimizing our cost function. What it does, it's very important that it helps in minimizing our cost function, which is j of theta 0 and theta 1. Recall that in previous video, in case you haven't seen, link will be in the description box below, so be sure to check it out. So in the previous video, our goal is to minimize our cost function, which is j of theta 0 and theta 1, because it is an error function, so we have to minimize it as possibly as we can be. Okay, so gradient descent is nothing, it is an optimization algorithm that helps in minimizing our cost function. Okay, now let's take a look at what gradient descent algorithm does. It starts with some values of theta 0 and theta 1, and recall that theta 0 and theta 1 are its parameters, so you can think of it as a theta 0 and theta 1 are called as parameters, and it starts with some values of theta 0 and theta 1, and it keeps changing those values and until and unless it reach out to the global minimum. Okay, what it does, it starts with some values. It starts with some theta values, theta 0 and theta 1, which is the parameters of our linear regression. It starts with these parameters, and it keeps changing our theta values to reduce our cost function until and unless we reach out to the global minimum. And you might be thinking, what is this, Ayush? To reach out to the global minimum? What is this? So let's take a look at an example so that you can get a better intuition about reach out to the global minimum. So here in x-axis we have our theta 0. Let me highlight that. In x-axis we have theta 0, and in y-axis we have theta 1, and in z-axis, vertical axis, we have our cost function, and it's bowl shaped. Our cost function is a bowl shaped. And what the gradient descent will do is that, let me take the black pen. So here let's say this is the initial value of our theta 0 and theta 1, theta 0 and theta 1, and what the gradient descent will do in first iteration, it take one step, and then second, third, fourth, fifth, etc., and it keep changing our theta values until and unless it reach out to this global minimum. And so it reduces our cost function, and this theta values are good to go. Okay, so what does it do? It keep changing our theta values, and it keep changing those until and unless it reach out to the global minimum, which is here at the black point. Okay, I think that you got a better intuition about the global minimum. Now one thing more, notice that the step taken at each point, let's say from here, we've started from here, is the learning rate, or alpha. It's called the steps taken, the size of the steps taken. Let me write this, the size of the steps taken, is called our learning rate, or alpha. Okay, so why does it call a learning rate? You can see here that our theta 0 and theta 1, or we can say parameters, are learning. Our parameters are learning, so we can say the rate that the parameters are learning are called learning rate. Just think about it, the rate at which our parameters, which is theta 0 and theta 1, are learning, is called our learning rate, or alpha. Okay, now let's take a look at how do we compute our gradient descent. For computation of a gradient descent, we have our favorite this. It is also easy, so just wait for some time here. Now here we have our j here. What is j here? We have to update the j values for j equals to 0 and j equals to 1. We have to simultaneously update our theta values. It means first of all theta 0 and then theta 0 and then theta 1. Okay, so just keep it aside that j would be the simultaneously updates of theta 0 and then in second theta 1. Okay, now let's keep this picture aside and see on that what I'm going to do here. First of all, what is this here? We have talk about j equals to 0 and j equals to 1. I think that you're confused. I think so. So when theta equals to 0, it is something like this: theta 0 minus the learning rate, the partial derivatives of our theta 0, our cost function. Okay, and here we have the theta 1. Okay, and theta 1 minus our learning rate, partial derivative of our theta 1, j of theta 0 and theta 1. Okay, now you understand what is j here. J is 0 or 1, and we have to simultaneously update our j. Now what is this? What is this? This is our assignment. This is not equals to, this is assignment that we are assigning to the here theta value, theta j, and we are and this is the learning rate that we have talked about, that we have to start with some initial value. We have to start with some initial value from here to here, here, and the size of each steps taken is called alpha, or we can say that the parameters that are learning and the rate of a learning is called a learning rate, as our parameters theta 0 and our theta 1 are learning. So at which rate they are learning? They are learning at learning rate. So the rate by which it is learning is called a learning rate, or we can say the size of each step taken is called an alpha. Okay, now I think you are clear about alpha. Now what is this? This is the partial derivative. This is the partial derivative of our cost function, and this might confuse you. This might confuse you. Just leave it aside. If you don't know calculus, it's okay. We are taking here the partial derivative of our cost function. But if we talk about the gradient descent for a linear regression, it will not be there. So don't worry about it. Just see here that we are taking the partial derivative of our cost function, which is j of theta 0 and theta 1. Okay, now here let's take a look at gradient descent for gradient descent algorithm. So here what we are doing, we are for j equals to 0 and j equals to 1, we have to update our theta values. Okay, now here we have just recapitulate again that this is our learning rate, and we are taking the partial derivative of our cost function, which is j of theta 0 and theta 1, and we have to repeat this process until it converges or reach out to the global minimum, and with for 0 also and for 1 also. Okay, now let's take a look at choosing our alpha value. It's a hyperparameter. It's a hyperparameter. So choosing this is very important role in this, because we have to tune this. We have to tune this. What we have to do, this is our alpha value, which is a hyperparameter, and we have to tune this. It means we have to choose other values and take this. Now let's take a look at when we choose our alpha value. When we choose our alpha value too slow or too small, the gradient descent can be very slow, and it takes a long time to be converged. Okay, so you don't have to choose alpha is too small, so you don't have to choose alpha too small. And if you choose alpha too large, what it will do? It will overshoot the minimum. What does it mean, Ayush? So let me take the pen and draw. Let's say this is my bowl shaped cast function, and let's say it starts what pen here, yeah, it is our initial values of theta 0 and theta 1, and it go from here, then here. It will overshoot something like this. Okay, it will overshoot the minimum and it will never converge. Okay, now I think that you got a better intuition about choosing alpha value, that you don't have to choose too small, you don't have to choose too large, you only have to what to do, you have to tune your alpha. It means as alpha is a hyperparameter, so you have to tune and take different values and see which alpha value is best for your model. Okay, I think most of the cases 0.01, 0.001, 0.0001, it's okay, whatever you have to tune and take a different values for your alpha. Okay, now gradient descent for a linear regression. Now it's time to learn about the gradient descent for a linear regression. So first of all, what we have gradient descent, this it changes something little bit and it comes to this. So what is this? Here we have this all is the partial derivative of our cost function, which is j of theta 0 and theta 1. Okay, I have that just see here that we have removed we have calculated the partial derivative of our cost function, and we are done with this. Okay, now similarly we can write theta 1 for this, and what we are doing here is that we are multiplying at last with x. Why? Due to the derivative, due to the derivative. Okay, now again I'm saying that this is the partial derivative of our cost function, as doing mathematical equation is out of the scope of this course, so that's why I'm not doing that. But if you're a calculus student, you can simply calculate the partial derivative of our j of theta 0 and theta 1, and you will get these values. Okay, now I think that you got a better intuition about a gradient descent. You are familiar with alpha value, choosing alpha value, and also tuning, and also you are familiar with a gradient descent for linear regression. Now it's time for implementation of our gradient descent. So without wasting time, let's get into it. Jupyter Notebook. So I'm on my Jupyter Notebook. So first of all, let's import all the necessary libraries, numpy as np, and import pandas as pd, and then import what? Matplotlib .pyplot as plt. Now let's run this. I have my data sample, so let me pd.read csv. I have sample data, sample data.csv, and let's categorize our data into x's and y's. So data, equals to data dot ilog, then we say 0, and again y equals to data dot ilog, then we can say 1 here, and okay, so we can plot it. If you want, plot that as scatter x y. Okay, now also what you can do is that plot dot show. So without now, but I don't want this picture, so I don't want, just for showing you all. Now we have this. Now it's time for defining gradient descent. Defining gradient descent, DESCENT. Then it takes theta values, theta 0, and then it takes theta 1. Let's take theta 1, and it's take alpha value, alpha, how many iterations, and then x's and y. Now first of all, let's m equals to the float of length of x, and then y prediction equals to the theta's, it's a hypothesis, so theta 0 plus theta 1 times x. Okay, now it's time for taking out the derivative for a theta 0, for derivative of our theta 0. So how we can do this? So minus 2 by m, here m is the number for training examples, minus 2 by m, so times our times sum of y minus y predict. Okay, now let's take it out the derivative for theta 1, and it's also the same, but only the times x, so 2 by m times our sum, and we can think of it as a x here, times our y minus y predict. Yeah, okay, now we have done this all. Now it's time for updating our theta values. So first of all, let's update our theta 0. So for updating our theta 0, what we can do, minus our alpha times our derivative, that it is nothing but we have to implement the formula. You can see here that we are implementing our formula here. You can see though that now we are derivative we have here theta 0. Now it's time for updating our theta values of 1, theta 1, and again we have to do theta 1 minus alpha times our d theta, d theta 1. Okay, now we can return our theta values because the parameters are learning and the parameters are theta 0 and theta 1. Now we can return this. So now we are done with our function. Now we can call this function. Let's call this, and first of all 0, let's give it as theta 0 equals 0, theta 1 equals also to 1, and let's say alpha equals to 0.0001, and iteration should be 1000, and anything you want, and our x that we have categorized, and our y. Now our theta 0 equals to this and theta 1 equals to this. So I think that you got intuition about how we can implement this on our Python programming language. So that's it for this video, and I hope that you have got enough knowledge for gradient descent. So thank you for seeing this video. Till then, bye bye.